Are all participants joined? I can hear you. You are mute.
I think we still miss one of the president participant. Let me check.
But somebody joined with iPad. I see
iPad.
that.
Yeah, yeah. So what's the name of this participant?
Okay, so maybe you can start. Okay, it's
yeah.
time.
Okay. Okay.
Okay, so good luck.
Thanks a lot. Thank you.
To all of you.
Okay. Yeah. Okay. So good morning, everyone. My name is Xin Wang. I'm from China Agricultural University. I'm the chairman in this session. So I'm working on Wageningen University and research for tomato robot project. And the first presentation will from Egan. The topic of this presentation is optimal tuning of the SMC parameters for two-link manipulator co-simulation control. So, Egan, now I will give you the floor and please take your time.
Okay, thank you.
Okay.
Good morning, everyone. My name is Sinan İlgen. I'm attending electronic conference from Turkey, and I am a research assistant at Karatay University in Konya, in Department of Mechatronics Engineering. I will talk about today our paper, which is entitled by optimal tuning of the sliding mode controller parameters for a two-link manipulator for simulation control. In this paper, we try to present the trajectory tracking control of two-link planar robot manipulator using Adams and MATLAB softwares with co-simulation operation. These are the contents of the presentation. Firstly, a brief introduction I will give, and then the details of the study will be explained step by step. And lastly, I have a conclusion and perspective parts. Let's start with the introduction part. As you know, as everybody knows, the robot manipulators have widely using for a wide variety of basic industrial operations, such as material handling, machine loading, or welding, etc. There is lots of examples. In general, the robot manipulators usually consist of rigid links, have connected each other by the joints. These joints that allow the motion of the neighboring these rigid links. The robot manipulator have easy installation, easy usage, and they have high mobility in the industrial areas. In general, when we check the literature, 2 or 3 degrees of freedoms manipulator system is commonly used for different applications. Also, there is some studies on the with 4 or more degrees of freedom have also been reported in the literature. First step of our study is system modeling, because system modeling is a very important part of these robotic systems. In our study, for virtual prototype of the manipulator, we use Adams software. The first step is modeling in Adams, and then after we Adams process, the designed manipulator is exported to the MATLAB Simulink environment for carrying out the controller implementation. And then finally, co-simulation stage is performed to simulate the movements of the manipulator. And these are the screenshots of the manipulator from Adams environment. 3D dimension, 3D view of the robot manipulator is like that. These are taken from Adams software. when we look to our manipulator model, the two-link manipulator is able to move only X and Y direction. We can think like a coordinate system. Our system, as you see in the picture, there is two inputs. These are T1 and T2. They are torques of the actuators. And we have to control two outputs. These are joint angles, theta 1 and theta 2, as you see on the picture. There is some system parameters it's on for robot manipulator. These system parameters are defined in atoms. You can see on the table, for example, mass of the links or length of the links. And the unit of the torque or angle of the joints. These all parameters are defined in Adams environment. I want to give a short summary of the co-simulation methods. In co-simulation methods, as you see in the picture, the Adams software and MATLAB MATLAB software is working simultaneously. When in this operation, the output of the Adams model, output of the robot manipulator is at the same time is controller inputs for the MATLAB system. Yeah, we think Adams is represents the system and MATLAB represents the controller unit. Likewise, controller outputs of the system is input of the Adams model. This is the basic methodology for MATLAB Adams co-simulation methodology. When we export these 3D robot model into the MATLAB Simulink environment, you can see in the right side picture, there is a orange box is, the manipulator comes to the Simulink environment like a box, as you see the orange box in the right side picture. And the other side of the picture is completely controller design of the system. We can look to methods and technologies parts. Firstly, in MATLAB Simulink sites, we try to create this block diagram for the system control. As you know, there is a, for robots movements, there is a transformation between position and angles of the joints. These equations named as kinematics. Here we have to use inverse kinematics because the manipulator should go to the our desired position. To perform this task, we have to attain the suitable joint angles in on the picture theta 1 d and theta 2 d. The equations of the inverse kinematics are manually calculated, and then these equations are embedded in MATLAB Simulink like that. After we get the joints angles, suitable joints angles, the controller procedure will start. As you see on the block diagram, we used two different type of controllers. One of them is sliding mode controller like SMC, and as you know, the other controller type is most generally mouse controller, PID controller structure. Again, same picture. These are the controller hierarchy on the MATLAB Simulink environment. I want to give a brief summary about the sliding mode controller. Sliding mode controller is a special type of variable structure control systems. It's generally used for the nonlinear systems. And Russian science-man Emelianov and Utkin is the first working with the sliding mode control, is the father of the sliding mode control, we can say that. And these controller type sliding mode controller has some advantages like insensitive against what are these? For example, parametric change of the system. If there is a parametric change of the system, the controller mechanism can be behavior insensitive. The other insensitive is external disturbing effects or errors in the modeling. The sliding mode control is completely insensitive against these disturbances. Expectation, what we want to do in this study, we have two scenarios for our robot manipulator. First one is 2-position control, and the second one is 5-position control. For the 2-position control, we try to implement of PID and sliding mode controller structures at the similar conditions. And scenario 2, just be focused on the sliding mode control, which we try to optimize the coefficients for the controller to get better performance for the robot manipulator. At first, 2-position control, we think like that. We put the robot manipulator on the origin in the XY coordinate system. And the end effector position of the robot manipulator is in X direction 0 and in Y direction 350 points. We want from the robot is it should go the first point and second point. We have 2 positions. First point is 250 point in X and Y direction, and second point is 50 in X and 200 in Y direction. These are the first scenario. We used PID and SMC control structures. It is performed on the MATLAB Simulink environment, and we have to we defined the required parameters for also PID and SMC is occurred by using response optimization toolbox on the MATLAB Simulink environment. For scenario 2, again the initial position is same, but in this scenario we wanted to make a bit difficult for the robot movements. We defined 5 different positions as you see in the table. For this one, just we used sliding mode controller. Also, we performed these control structures on MATLAB Simulink, and also we defined the all coefficients, all parameters for sliding mode controllers under response optimization toolbox. In difference from scenario 1, in response optimization toolbox, we compared 3 different optimization algorithms. Gradient descent, pattern search, and simplex search. These all optimization algorithms is ready for use on the Simulink environment. When we check the results for the first scenario, 2-position control, as you can see, the robot manipulator is put on the origin of X and Y coordinate system. At the same condition, the blue one is sliding mode control, as you see, and the red line represents PID controller. When we compare these results, the sliding mode controller is more efficient than the PID controller performance at the same time. We can check the coordinates result. This picture represents the X coordinate system. Firstly, I want to share this information. We planned the total movement of the robot is 10 seconds, and in first 5 seconds, the robot should go to first location, and then between 5 and 10 seconds, the robot should go to second position. If we check this graphic, for green line for reference, the sliding mode controller has better performance than a PID control structure. And for the Y coordinate is shown in this figure. Also, there is a good performance with respect to SMC sliding mode controller compare with the PID. And these two images for the fast portraits of the sliding mode control, these two graphs is important for the sliding mode controller structure. How can we understand this? How can we explain this graphic? For first 5 seconds, movement 1, location 2, for location 1, the blue line is the important thing is the error is converged to 0 at the beginning of the movement. It is 0, but while the coordinates of robots is changing, the error will become, I can show like that. At the first it is 0, but with some time the error is not 0, but at the end of the position the error and derivative of error is nearly 0. Also for the second location, at the end of the movement the error and the derivative of error is converged to 0. These images for theta 1. For theta 2 also there is 2 parts, location 1 and location 2. Both of the movement sides, the error and the derivative of error is converged to 0, as you can see. Let's check the 5 position control results. Again, we put the robot manipulator on the origin in the XY coordination. As I said, there is totally 5 locations. There is totally 4 graphs because, as I said, I have used 3 different optimization algorithms, and extra there is no optimization here, just trial and error methods. We want to compare 4 of them. And when we check the graph, the pattern search is orange line is very bad performance at the same condition for these optimization algorithm. And then we check the others optimization, gradient descent or search simplex, and trial and error methods coefficients is better performance than the pattern search optimization algorithm. If we can check the, again, 5 position control for X coordinate, as you can see, the one of them, just pattern search, is a bad result at the same condition, but the other optimization method or non-optimization results have a good performance for 5 different position control. Also, the same results for the Y coordinates. The pattern search result is better than compared with the X coordinates. These are the results for the 5 position control. Conclusion, why we did this study. When we see in the literature, there is a lack of knowledge in Adams and MATLAB co-simulation operation. There is a few studies. There is lots of studies for different softwares, for example, SolidWorks and MATLAB, or ANSYS and MATLAB. There is lots of work, or CATIA and MATLAB. Again, there is lots of study, but there is a lack of knowledge in Adams and MATLAB co-simulation. We think that there is these co-simulation operations presents an efficient solution in simulating and controlling of the nonlinear systems, such as robot manipulators or other nonlinear dynamic systems. We think that it can be, these studies can be based for the future works about simulation and control of the robot manipulator. What is our future projections? This study is not finished, of course. We have to improve the controller performance, for example, decreasing settling time, or we have to acquire no overshoot results. And we will try to make these control operations with under payload. In this study, there is no payload for our scenarios. And move to we want to try to robots to move different positions with some different payloads. And thank you for your attention. If you have any questions or comments, I can do. Thank you very much.
Okay, so thank you very much, Egan, and thank you very much for your nice presentation. So now it's okay. So now it's question time. So is there any questions? You can open your microphone, or also you can put your questions in the chat. Okay, so I have questions first, maybe. So in slide 12, I see a picture from your presentation, and you said this effect of from SMC model controller will be more efficient than PID. So can you explain it?
We define the controller parameters on the response optimization toolbox at the totally same conditions. This is a reduced software. We just run the program and get some coefficients for also for PID or SMC. We didn't do any changing of these parameters. We can apply to the system. The results of the system is like that.
Okay, but you said it's more efficient. It means that you need not change any parameters from your model. Yes. Okay.
Yes.
Yeah. Okay. So if it's not any other questions, I will thank you, Egan, and I will give the floor to Kristen Takas. Kristen Takas, are you here?
Good morning. Yes, I'm here.
Yeah.
Can you hear me?
Yeah. Yes. Can you share your screen?
Yes. A moment, please.
Yeah. Okay. Yeah. Okay. So now I will give the floor to Kristen Takas. The topic of his presentation is control of robotic arm with visual system. So please take your time. Good luck.
Thank you. So good morning, ladies and gentlemen. I would like to quickly introduce myself. My name is Christian Takac, and I'm a first-year PhD student at the University of Žilina in Faculty of Electrical Engineering and Informational Technology at the Department of Mechatronics and Electronics. Now I would like to share with you our paper on topic control of robotic arm with a visual system. This paper was created in collaboration with my colleagues. In this presentation, I will talk about the design of a sorting system that is able to sort objects based on their color, shape, or its combinations. Next, I will talk about the analysis of the used hardware, searching methods and sub-algorithms, implementation to the lab environment, and testing the reliability of searching methods. The hardware design of the proposed sorting system consists of a camera with a lighting source, and robotic arm, and a superior computer. The left side of the screen shows the used camera sensor. The SIMIA camera is designed for a machine vision application in industry. Its resolution is 1.3 megapixels with frames per second rate up to 200 FPS. This camera is used for capturing an image of the workplace located in front of the robotic arm, and the camera is attached on a static tripod with a macro zoom objective. The right side of the screen shows the used robotic arm. The robotic arm from Dubot is a multifunctional 4-axis manipulator with the possibility of connection variables and devices. The robotic arm is intended mainly for teaching purposes. With this arm, the found object is transferred to a predetermined location with a vacuum suction cup or a pneumatic gripper. The configuration of the robotic arm was based on the analysis of its kinematic equations, operating modes, and communication with the superior computer. From this analysis, the location and the size of the workplace was determined, which the size of this workplace is 20 by 10 centimeters. The left side of the screen shows the area in which the robotic arm can move, and the right side of the screen shows the robotic arm in the Cartesian coordinate system. After the hardware analysis, proposed software for the sorting system was designed in the LabVIEW environment with a GUI. The graphical user interface of the sorting system is shown in the left side of the screen. The right side of the screen shows the block diagram of the proposed software. After the user selected the shape and the color of the required object, selected a type of the searching method, and enabling or disabling the image balancing sub-algorithm, and pressing the start button, the main software of sorting algorithm begins. The workflow of the algorithm is as follows. The camera captures a scene of the workplace on which are the objects randomly situated. Then the captured image is proceed with the image balancing subalgorithm. Then the selected searching algorithm or method starts the searching the selected color or the selected shape of the object. If the algorithm doesn't find any matches, then an error message occurs on the GUI. If the algorithm does find a match, then calculates the center of mass of each matching object in the image. This value is in pixels, so the algorithm transforms the values to the corresponding form for the robotic arm, which picks up the found objects and put them aside. As a last step, the endpoint of the robotic arm moves back to its home position, which does not interfere with the view of the robotic arm. Next, I would like to show you the concept of some used subalgorithms. The left side of the screen shows the block diagram of the surface height mapping subalgorithm. The height mapping of the workplace uses an effector with a mechanical bottom, and it is needed to assess if the work area is absolutely flat or to compute a lookup table of the height coordinates for each point of the workplace surface. In the selected measuring key points, the workplace, the robotic arm decreases its height coordinates until the button touches the surface of the work area and changes its logical state. This state is evaluated through GPIO pins of the robotic arm. The actual height coordinates are saved to a calibration file, and refinement of this height map is reached using a bilinear interpolation of measuring key points. The right side of the screen shows a block diagram of the position controlling subalgorithm. Later in the process of attaching the object to the suction cup, we must consider the Z dimension of the object. Then the sub-algorithm processes data from object detection algorithms. One of the main output value of these algorithms is the center of mass of the desired objects. The sub-algorithms initialize the suction cup compressor before transferring the object. Then the conversion of obtained data from object detection algorithm into the processable data type for the robotic arm is executed. Logical signal driving the compressor of the suction cup is coupled with the motion of the robotic arm. After the object is attached with the suction cup, the arm moves to a predetermined location where the suction cup is turned off and the object is released. Since some algorithms use segmentation based on color information, we must correct the input images to provide a white color balancing. So the shift of the color spectrum is in the captured image occurs because of the CMOS sensor of the used camera and the used LEDs in the light unit emits a light in the blue part of the color spectrum. So correction of RG and B gains in the camera sensor must be set up in the hardware way, or the accurate image must be balanced by the software way. In the simple way, the principle of the operation of color balancing subalgorithm is to calculate the correction heights for the individual pixels of the R, G, and B layer based on a selected pixel in the image. Applying the white balance serves also a normalization of input images in an aspect of a color sense. The left side of the screen shows a block diagram of the searching method based on shape factor subalgorithm. The subalgorithm first converts the image from the RGB space to the HSI and extract the intensity layer, which contains the information about the presence of objects in the image. Then the normalized compactness is calculated from each object in the modified image. Based on the value of normalized compactness, the subalgorithm is able to define the selected object. The shape factor computes the compactness of each object segmented from the image based on equation 1. But to normalize these values to interval from 0 to 1, we often use a formula for normalized compactness based on the equation number 2. The right side of the screen shows a block diagram of the pattern matching subalgorithm. This method search also requires that the image must be converted from RGB space to HSI before the process of searching for object begins. And unlike the shape factor method, this method requires a template that contains the shape of the object. The principle of operation of this method is based on moving the template across the image according to normalized cross correlation technique, while at each point the algorithm calculates the correlational score. Because the underlying mechanism for correlation is based on a series of multiplication operations, the correlation process is time-consuming. The left side of the screen shows a block diagram for the geometrical matching to algorithm. This geometrical matching search method, like the previous method, required a template for detecting object and converting the original image. The principle of operation of this method is that the algorithm extracts the information of the curves from the template and then compares the curves and their coordinates in the grayscale image according to the gained information of the template. The algorithm recognizes objects based on their geometric shape, and the algorithm calculates the correlation score of each object. The right side of the screen shows the block diagram of the color-based object searching method subalgorithm. This method allows the user to select an object of a specific color from a scene. The sub-algorithm first converts the image from RGB space to highest I and extract the hue layer, which contains the information about the presence of certain colors or a wavelength range in the image. If the position of each color in the hue layer is known, then the sub-algorithm can execute the global thresholding of this layer to detect the object of a specific color. After a basic morphological operation, the sub-algorithm computes the center of mass of each object. The proposed sorting system in form of the laboratory setup for testing the reliability of used searching methods is shown in the left side of the screen. The testing was focused on measuring the reliability and speed of previously mentioned searching methods for searching a specific objects in the captured image of the workplace. The right side of the screen shows the comparison of captured original image of the workplace and the balanced version with the phantom objects in form of simple geometrical shapes. In the center of the screen is shown a comparison of the testing, the reliability of each searching method. The left side shows a bar chart of correctly detected objects of each used method. And the right side of the screen shows the bar chart of searching time and average searching time of each used method. The result of that measurement is that by using the color balance sub-algorithm on the original image, we can increase the percentage of correctly detected object, minimize the number of falsely detected objects, and speed up the average object search time by highlighting the edges of the searching objects. So in this presentation, the design and analysis of a sorting system was described. So it is possible to sort objects on the captured workplace by color, shape, or their combinations. In the GUI, the user is able to choose which of the mentioned method is used in the object searching process. The software of the sorting system was designed in the lab environment, and also the color-based searching methods, the searching method based on shape factor, the color balancing sub-algorithm, and a sub-algorithm for controlling the robotic arm were implemented in this environment. Thank you for your attention, and feel free to ask anything.
Yeah. Okay, thanks, Kristen. And so now it's question time. Is there any questions for him? And please open your microphone or put your questions in chat.
May I ask a question?
Yeah, please.
Yes, I'm from Turkey. I'd like to give regards from Turkey. My question is, you use a simple robot. Is it possible to use very complex robot for this image processing algorithm?
It is possible, and the method of using a more complex robot is based on the communication between the used arm and the superior computer. So it must know the communication packets of for the driving the robotic arm.
You mean the system is universal? You can use for every robot?
Yes, by changing some of the, as I said, of the communication packets.
Okay, thank you very much. It is
You're
very
welcome.
good work. Congratulations.
Thank you so much.
Okay, is there any more questions? Yes, maybe I also have questions for your visual system. So you said your system is use some algorithm, color-based balance algorithm. So now it's only used in blue color light, or also you can extend it to different color light. And how you consider the illumination issue? Yes, please.
So the first part of your question, this color balancing algorithm is universal. It works on the principle of that the algorithm choose a white pixel, and from this pixel the height of each pixel from R, G, and B layer is like updated. So it is possible to change the red or blue or the green color.
Yeah. Okay.
And
So yeah, please.
and you ask for the illumination.
Yeah.
I sorry, but I don't understand this part of your question. What did you mean?
Just like now, you do the experiment in the indoor environment.
Yes.
So have you considered about if you put your object into outside, what will be the issue for this?
We don't experiment with this environment where the light could change, but it is possible that each searching method could find more phasally to matches of the objects, or could not find the required objects.
Okay. Yeah. Okay. Thanks a lot. Thank you very much. Thank you for your nice presentation, Kristen. Yeah.
My pleasure.
Okay. Okay. So now I would like to change to the next presentation. So Andruski, are you here? Maybe you are mute. Yogita Andruski.
Yes, yes, yeah. But the presentation will be by Professor Sertak.
Oh, Sertak. Okay, Professor Sertak. Okay. So good morning. Can you share your screen and?
As I know, the program changed, and we are going to present our study. Am I right?
Yeah. Yes.
Okay.
Yeah. Okay. I will try to do a brief introduction, and you can start later. Yeah.
Okay.
Okay. So this topic for this presentation is controller gain tuning of a non-holonomic mobile robot while neural network predictor. So the practitioner is Sertak. Yes, Professor Sertak. And so now I will give the floor to you, and please start. Thank you.
Thank you. Okay, thank you for your presentation. My name is Sertaç Savaş. I am assistant professor at Kaunas University, Mechatronics Engineering Department from Turkey. And the name of our study is Controller Gain Tuning of a Non-Holonomic Mobile Robot via Neural Network Predictor. First of all, I want to talk about the importance to design systems for blind people to increase their integration into their social lives. So in that study, we aimed to design a robotic system and also a control approach which will enable blind people to move from one place to another. And it is decided to design a mobile robot can go to a target point with the least error on a certain trajectory and in a working environment known with its obstacles. So in this direction, we designed a analytical kinematic controller, and it is proposed to determine the control gain parameters using artificial neural network. And we made some real-time experiments to examine the tracking performances of the artificial neural networks. And we made these experiments for 2 different platform conditions, with and without obstacles, and for 2 different target points, A and B. In section 2, I want to talk about experimental mobile robot and mobile robot platform. We used a mobile robot designed by National Instruments called Robotic Starter Kit. We selected this second version of this robot, and also it is called DANI, the abbreviation of Data Acquisition National Instruments. It is designed a mobile robot for real-time applications. It's an out-of-box mobile robot, and it has a control card called Single Board Trio 9632, and it is also developed by National Instruments. And this control card has 2 processors. The first one is 400 megahertz processor, and the second one is FPGA processor, Xilinx Spartan FPGA processor. This processor is really suitable for real-time applications with a high hardware communication speeds, especially in hardware communication speeds, and also a motor driver, a dual motor driver, a power regulator, an interconnection card, 2 incremental optical encoders, and of course a battery we have on the robot. And in figure 1, we can see the structure and the basic elements of the mobile robot. Also, we made some additions to the mobile robot, an access point, and to obtain the wireless communication between computer and mobile robot, and a plate with 2 markers. We used this plate for image processing to make the localization of the mobile robot, posture of the mobile robot, and heading angle, orientation to determine the heading angle of the mobile robot, with a camera mounted on the ceiling of the lab, which our working environment place built, and a LED light source. It is important to obtain a stable intensity for the light on the plate for image processing. Also, a portable power bank to supply power to the access point and LED light source. And in figure 2, we can see the final version of our mobile robot and the hardware additions. And we built a mobile robot platform in our lab, El Jaziri Mobile Robotic Systems Lab. A camera is mounted in the ceiling of the lab, as I said before, for the localization of the mobile robot to determine the posture of the mobile robot, and orientation, the heading angle of the mobile robot for image processing. And this is called simulated GPS. It's like a bird's eye. It has a field of view of bird's eye. And we used an ultra-wide angle lens, 120 degrees angle with this angle for image processing. And we can see that it needs a hardly distortion correction because of this ultra-wide angle lens. In section 3, I want to talk about the controller design. As I said, we made an analytical kinematic controller. We designed a kinematic controller. And you can see in the following equation the control velocities of the mobile robot. This is called upper level control. You know, in real time, we have two parts for the control approach. And this is the upper level control. Also, we made for real-time experiments some lower level control, just like DC motor velocity control. And in the equation, we can see K1, 2, and 3 as the control gain parameters. And our we proposed to tune these control gain parameters using neural networks. And in figure 6, we can see a usual closed loop control block diagram. And our system, you know, it's a mobile robot, and the output of the mobile robot is posture. So at the beginning of the control loop, we are trying to eliminate the posture error difference between reference posture and actual posture, and we multiply this difference matrix with a transformation matrix. You know, we are working on a horizontal plane, so this transformation matrix is a Z rotation matrix. So the controller uses this posture error on the local coordinate system of the mobile robot and tries to eliminate while producing the control velocities, angular and linear velocities, and mobile robots produces the new actual posture. And then we made neural network predictor design. As I said before, we proposed to predict the control gains using artificial neural networks. And we made 90 real-time experiments. These experiments done for, we will see in the following slides. We made these experiments for the target point A and for the platform without obstacles. And we obtained 90 real-time data for posture error E1, 2, 3, and for different control gain values for K1, 2, 3, K1, K2, and K3. And this input-output relationship is taught to two different artificial neural networks. And these were multi-layer perceptron, MLP, and radial-based neural network. These are usually, they are commonly used for the fitting applications, for predicting applications. And finally, we obtained the black box network models for these experimental data. Also, we determined the parameters of the neural networks during a lot of training processes. We made these, the training processes are carried out for different hidden layers neural number and for three different training algorithms and for 3 different activation functions. Also for RBNN, radial-based neural network, the training processes are carried out approximately for 100 different speed values. So in table 1, we can see the parameters which gives the lowest training errors. So we are going to use the networks with these parameters to determine the gain values of the controller. And in the second part, we determined the control gain values, as I said. And now we applied 9,600 different gain values as a simulation way to the network inputs. And we examined the outputs of these networks as the control gain parameters. So we had the chance to do a lot of trials with the control gain parameters to examine what the posture errors they will produce. It's not possible to do 9,600 experimental studies, but we were able to do these simulation studies with the black box of neural networks models. So in table 2, we can find the control parameters, which gives the lowest posture error, mean squared error, values. So we will use these network models and these control gain parameters in the experimental studies to compare the tracking performance of these gain parameters produced with these neural networks. So final experimental studies we carried out. These studies carried out for 2 different platform situations we will see in the figures following, with and without obstacles, and 2 different target points, A and B. And we developed 2 programs. The first one is localization and trajectory planning program. This program developed in a previous study of our teammate. And the main focus of that study is about the program trajectory tracking control program. The control cycle is nearly 35 milliseconds. And as you know, it is really suitable for the real-time applications. And we carried out these experimental studies for the reference linear velocity 0.1 meters per second. While doing the control process of a mobile robot, you have to define one stable reference linear velocity. And we obtained the data for neural network training for the reference linear velocity 0.1. So we we will focus for the results, especially for this linear velocity. But also we repeated the experiments for a lower and higher one, 0.07 and 0.13 meters per second, to just examine the tracking performance of the control gain parameters. If these parameters is suitable for tracking the trajectories, or do we need to determine again the control gain parameters for these linear velocities? And figure 7, we can see the trajectories tracked with the control gain parameters produced with MLP on the left hand and on the right hand, predicted with RBNN, radial basis neural network. And in all figures, in all graphics, we can see the reference trajectory, map boundaries, first of all, as the blue line, and reference trajectory, and trajectories tracked with different reference linear velocities. They are all in the same figure. And this is the map without obstacles for the target point A. If we focus on these graphs, we can easily see that when it is not a challenge path, for example, a linear path, it is easy to track the path for each controller. But if we have sharp turns, the challenge starts, and the heading angle, the orientation of the mobile robot starts to oscillate. So we can easily see the amplitude of the oscillation, A and B. The RBNN control trajectory, I mean the gain parameters produced with RBNN, the amplitude of the oscillation is significantly lower, we can see from the figures. Also in figure 8, we can see easy path, a linear path. So we can just say the performances, tracking performances of all gain parameters is similar, close and high. They track the path really successfully. But again, in figure 9, we can see the platform with obstacles for the target point A. And again, for a linear path, it is easy to track, but in turning points, again, oscillation starts. And as we can see, RBNN controlled mobile robot heading oscillation is lower. And finally, in figure 10, we can see the platform, the map with obstacles for the target point B. And again, we can see the faster response of RBNN controlled mobile robots. So finally, for the conclusion, we designed kinematic controller and proposed to predict the control gain parameters with this for this controller. And we made some experiments to investigate, examine our proposal. So we observed that the RBNN neural network predicts the control gains better than MLP, and these control gain parameters have better tracking performances, especially faster response to sharp turns. And also we carried out experimental studies for a lower and a higher reference linear velocity. And for a lower one, we saw that the performances are close and high, no problem. But for a higher reference linear velocity, the mobile robot orientation started to oscillate, but still the amplitude of the oscillation was lower in the RBNN. But we can say that it should be redetermined at rising reference velocity. The control gain parameters must be redetermined. And in future studies, we can suggest by performing a flexible localization approach, experiments can be carried out in a larger workspace or for outdoor applications. Also, the controller design can be improved. Integral and derivative control effects can be added to our controllers. And also, different control structures can be tested for this concept of research. And also, we thanks to our scientific research projects units of our university for their support to this project, the study of this project. And thank you for listening. That's all.
Okay, thank you for Mr. Sertas. Now it's a question time. Is there any questions? Please open your microphone, and also you can put your question in chat. Okay, so maybe I have a question first. So Mr. Sertas, I would like to ask, because now you set the camera on the ceiling of the lab. So I would like to ask if the robot enter to the blind zone of the camera under some certain case. Is there some strategy to do that from the robot? Yeah.
In fact, we wanted to use the advantage of studying in a lab. So for an indoor application, just like a platform in the lab, we wanted to use the advantage to make the localization of the mobile robot with a, as I said, a bird's eye field of view. But of course, there are ways to make the localization. This is a search area for the mobile robot to make localization for achieving the localization problem. The first idea for this, it's a LiDAR sensor for indoor applications. But if you go for outdoor applications, you have to use GPS or assistant GPS for these applications. And as we know, these devices and these technologies is getting better day and day. And it's of course possible to use these flexible localization methods to take the mobile robots in other environments, working environments, and for other applications.
Okay, thanks. Is there any other questions? Okay, so if not, I would like to thank you very much for the nice presentation from Professor Sertas, and I will change to another topic. So, Mrs. Maria Gianna, are you here?
Yes, good morning.
Yeah, good morning. So I would like to give the floor to you. And the topic of this presentation is real-time path recognition and automatic control of educational smart car. So please start your presentation and good luck.
Please let me introduce myself. I'm a third-year PhD student at the University of Craiova, Romania, and this paper was done in collaboration with my colleague, Theodor, also a PhD student in the same department. The main topics of the presentation are autonomous driving research motivation in industrial and academic sectors, real-time image acquisition, processing and control for a scale model car, experimental results, and conclusions. It is well known that autonomous driving is shaping the future of automotive development. The main challenges are associated to the real-time perception of the environment and to the real-time processing of this data for vehicle control in dynamic environments. A real-time prototype of the road can be obtained using data from scanners, camera systems, and LiDAR sensors mounted on a vehicle. The vehicle control should consider avoidance of any immediate collision and determination of the path to destination. Industrial research in the autonomous driving field was also extended to the international academic sector. In the last years, the largest suppliers of automotive embedded systems launched through their educational programs different contests that involve the development of autonomous small vehicles. One of these contests is NXP Cup, Intelligent Car Racing, Competitions are held across Europe and North Africa, where student teams race their cars for the fastest time, running on a track of curves, intersections, hills, and straights. As we see, a track model, the pattern is white and the edges are black. The development of the car includes the hardware platform manufacturing and the microcontroller programming. The paper presents the real-time path recognition of the track and the control of the smart car built for this contest. In order to perform the real-time path recognition, real-time image acquisition is needed, and this is done using a camera sensor. This camera sensor module provides a TAOS 128 pixel linear array sensor and a lens. The linear sensor consists of a 128 array of photodiodes, associated charge amplifier circuit, and the pixel data hold function that provides simultaneous integration for all pixels. The output from each pixel is an analog voltage proportional to the light intensity and to the integration time. Images can be acquired in continuous or one-shot mode. The acquisition algorithm was implemented on the microcontroller and is described on the left side, was done based on the timing waveforms from the camera sensor. The clock controls the charge transfer and pixel output, and the serial input defines the start of the data out sequence. The values from the pixels are read in this way. So firstly, the serial input is set to high, clock is set to high, serial input is set to low, and the analog voltage for the first pixel is read. After, all the analog voltage for all the other pixels is read based on the clock cycle. Of course, because we have an analog voltage, an analog to digital converter is used. At the end, the algorithm returns a buffer which contains the values from all 128 pixels. In order to better analyze the information acquired from the camera using the above algorithm, a Bluetooth communication between the car and the computer was established. During a run on the track, the vehicle transmits acquired images from the camera, and they can be visualized using a MATLAB interface. For example, we have here images from a straight path, from an intersection path, from a left curve, and from a right curve. The images show the differences between the white and the black zones of the track. It can be observed that the black edges are at least 3 times less in amplitude than the white zones. The pixel amplitude depends also on the light intensity. The output of the acquisition algorithm is provided to the processing algorithm in order to obtain the path recognition of the track. And the control of the smart car is based on the steering control and on the motor speed control, as it can be seen in this closed loop structure. From the processing algorithm results the path direction of the track. This is converted in a deviation relative to the center of the track with values between -63 to 64, where 0 is the center. This deviation is used for the steering control using a proportional gain. The command is saturated in a certain range based on the actuator works limit, and this is applied to the servo via a motor bridge. The motor speed control is done based on the information provided by the Hall effect sensors mounted on the wheels. The speed reference is defined in the initialization phase of the algorithm, of the control algorithm, and represents the desired speed of the car. This is influenced also by the deviation of the path direction. So if a curve is detected, for example, the desired speed reference will be modified because braking is needed. So this speed reference is then compared to the measured speed, and the PID adaptive control law is used. The command is also saturated in a certain range and is applied to the DC motors via a motor bridge. To keep the car on the track, the data acquisition, elaboration of decisions, and actuation of the car are performed in real time at every 2 milliseconds. As an example, in case the deviation has a negative value, it means that a left curve is detected, and the vehicle should firstly brake and then steer to the left side. The speed set point is firstly decreased for braking by using a variable proportional gain. Then the set point value for the left motor is reduced, while the set point value for the right motor is increased in order to obtain a speed differential control. For a right curve, the speed differential control is applied in the opposite way. Experimental results. The design car participated in the NXP Cup Intelligent Car Racing Finals in 2018. The parameters of the control laws were tuned during racing on multiple test tracks. The final track was assembled just before the contest. And from the official results, it can be seen that the car won the first place with a noticeable difference of 4 seconds than second place. The active learning approach described in this paper has been applied within similar academic competitions. The targeted groups were 3rd and 4th year students from the bachelor's degree program attending the embedded system courses. The grading comparison based on the exam results indicates that the students which took part in this learning approach motivated better their answers, completed their tasks with better results, and they were capable to explain in much more detail the implemented hardware and software solutions. In conclusion, this paper presents a successfully applied learning approach on embedded systems, considering a scale model vehicle used in an international educational program. Considering the main problems of the self-driving perspective, the presented solution for path recognition and control can be used for better understanding the risks and uncertainties which the automated vehicles industry faces in different driving scenarios. The presented learning outcomes show that this approach helps students to improve their technical abilities, their communication and teamwork skills, inspiring them for engineering careers and future innovation. The paper emphasizes the actual concerns in the industry of automotive embedded systems. High levels of automation are desired for vehicles to manage any driving scenario with no human intervention. Thank you for your attention, and if there are any questions.
Okay, thank you, Maria Gianna. And is there any questions for her? Please open your microphone or put your questions in chat. Okay, maybe I have a question first. Maria Gianna, I would like to ask, because this is a very meaningful competition. So what do you thinking about the bachelor? You said the bachelor student have a course for an embed system.
Yes.
Yes.
For
So
embedded
it's
systems.
yeah. So it's special for this competition, or it's a general course?
No, it's a general course, but normally from our university, for example, the student teams for these competitions are from third and fourth year bachelor's degree, when the embedded systems, when they learn the embedded systems.
Okay, so from this course, you will select some student to join this competition, or just?
Yes, I can select some of them, and of course, the students that want to participate, they want to accept this challenge.
Yeah. So, what do you thinking about from this competition? What kind of the skill the student can improve themselves from the course or from the competition?
From the competition.
Competition, yeah.
Especially the embedded system knowledge, programming knowledge, firstly, and also hardware knowledge, because, as I said, the design of the car includes also the hardware platform manufacturing.
Yes. Okay. So, do you have some a plan to set some course just for this competition? Because as far as I know, there are some university has some course just for some competition. Like in Wageningen University, they every year they will intend fire the robot competition from Germany. So they open one course for this competition. Is there any idea or plan to open some course like this?
No, I didn't think to plan such a course only for a competition. Usually when students want to accept this challenge to participate, the groups are somehow coordinated by professors, and yes, they can be considered as a class and they exchange knowledge.
Yeah. Okay. Thanks a lot.
Thank you.
Okay. Is there any more questions? Okay, if it's not any more questions, I would like to thank you, Maria Gianna. Thank you very much for your nice presentation. And yeah, so Darius, do you want to say something, or I just close this session?
I think that yes, as chairman, you can close.
Oh, your voice is quite low. Yeah.
Sorry. I think that as a chairman, you can close the session.
Sorry, it's still quite low for your side.
Strange. Just a minute. And now maybe better.
No.
Okay. So just you can close and that's it. Okay.
Yeah, yes, I can hear. Yeah, okay. So I would like to thanks a lot for all the presenter and all the participants in this session. And I will close this session and have a nice day. Bye.
Thank you. Have a nice day. Goodbye.
Bye.
Bye-bye.
Bye.
Hello, Bogdan.
We try to find the connection. Just
Everything is okay.
oh,
I can see you, you can see me, I can hear you, and you can hear me.
Sure. Therefore, I should wait, right?
Yes. The previous session ended a bit earlier because one participant was shifted to tomorrow session. So we have, let's say, now 37 minutes.
Okay, fine. Okay. I will wait. I will
Okay.
wait. Okay.
Okay.
Thank you very much.
Thank you.
Thank you very much.
What are you doing here? Good morning.
Good morning, Darius.
How is going?
Fine, thank you. We will start our session in 40 minutes. Yeah.
Yes, yes.
Session 2B. But I'm a little bit red. How to change it?
Okay. Just I think that two chairmen joined at the same session. So Bogdan, do you hear me?
But this session is B, yes?
Yes. So
this
yes.
one.
Yes, you joined correctly.
Okay, I can hear you just now.
Bogdan.
Hello, Bogdan.
Hi, Wojciech.
Your session is A. You should join to another link.
Oh, another link. Okay. What kind of link? Fine. Okay.
7A.
7A. Oh, okay. 7A link. Just a moment.
Okay. Previously, two chairmen joined at the A session.
Yeah.
Now to B.
Are
you at home?
Yes, I'm from home today. So I think next year we will meet maybe in Palanga.
I hope that
do something.
Many of participants will be vaccinated, and even those who will not, maybe they are able to travel. I don't know.
I will put some maybe external light. It will be better, maybe.
It's okay. It's okay.
Cool.
Not so red, not so yellow.
Not so yellow. Kate, come on here for a minute. Oh.
Hey.
Hello. How are you?
I'm well. Everything is okay.
Okay,
and
good.
You?
Thank you very much. Thank you.
Okay, so Beniusu is joined to another session, so he will he will be here.
And what's about Nima Georgie from Ireland? And
just give me some time, okay? I'm writing an email.
Should I just begin?
No. Please wait.
I'll wait.
Please wait. Our boss is calling for other participants. Waiting. What is the weather in Denmark?
It's very sunny.
Good.
It's a nice day to sit inside all day.
We have here in Poland good weather too. Very sunny, 21 degrees. Nice weather.
Yeah. It's only 15 degrees here, but it's nice. It's not too warm day in the apartment then.
Darius is calling. Can we start, Darius?
Yes. I think you can start, okay? And probably the rest of participants will join later.
Okay. So we can start right now. Good morning, everyone. Welcome to the session 2B, Untitled Electronics. I'm from Białystok. My name is Wojciech Wolędziuk. I'm from Białystok University of Technology. It's in Poland. It's a northeastern part of Poland called Greenland, lungs of Poland. So we are welcome to visit our region. Maybe in the future. Today's session is about electronics. We have 6 papers, 6 presentations. Today, the first one is novel analysis of inherent power supply rejection in switched capacitor converters. Professor Jacob K. Toft will present. So the floor is yours. You can start.
I'm just a PhD student, by the way. But
in the future,
maybe.
We are waiting for you as a professor.
Okay. Yeah, so my name is Jacob Toft. I'm from the Technical University of Denmark, and I'd like to present my work on inherent power supply rejection in switch capacitor converters. First, I'd like to give an introduction to why this is interesting, and then I will introduce the switch capacitor converter model that I've used in my analysis and talk about where the inherent power supply rejection is from. And then I will present some limitations to the inherent power supply rejection in switch cap converters and wrap up with some simulation results and a conclusion. So switch capacitor converters are widely used in integrated circuits to convert voltages to different voltage levels, and examples of applications are power conversions, converting battery voltage down to a lower voltage for more power efficient circuits, or bias voltage generation for example for micro electromechanical system sensors. And bias voltage applications, switch cap converters are often referred to as charge pumps. So in MEMS biasing applications, the sensing is often based on capacitive sensing, while high bias voltage improves sensitivity of the sensor. And to improve the SNR, the bias voltage must have a low noise. This is often generated by having a linear regulator that makes a low noise supply for the switch cap converter. And then the boosted voltage is in some applications filtered to further remove noise from the bias voltage. And then the bias voltage is applied to the MEMS, and there's a readout circuit. If the switch cap converter could attenuate noise itself, the specifications for the LDO or filter on either side of the converter could be relaxed and make the life easier for the designers. So switch cap converters are often modeled as follows: as a transformer with an ideal voltage gain represented by the transformer ratio M/N, and then an equivalent output resistance R out, which is equivalent to the root sum square of fast switching limit component and slow switching limit component. The fast switching limit component is given by the charge transferred through the switches in the converter and the on resistance of the converters, and the slow switching limit is given by the charge transferred by capacitors, and it's inversely proportional to the size of capacitors and the switching frequency. Sorry. In most switch cap converter applications, there's an output capacitance to reduce ripple, and introducing this capacitance creates a low-pass filter, which will attenuate signals from the supply as a low-pass filter, and this is the source of inherent power supply rejection that you can find in the switch cap converters. And I have not seen anyone else address this, which is why this analysis is novel. But something this model doesn't catch is implications such as direct AC paths in the topologies of switch cap converters and topology-dependent sampling rates. So, for example, first the voltage doubler topology. In phase 1, the switches S1 and S4 are closed, and the flying capacitor is charged by Vn. And then in phase 2, the switches S2 and S3 are closed, which creates the direct AC path from Vn through Cfly to Vout. The direct AC path is attenuated by the capacitive voltage division between Cfly and Cout. A different topology in the Pelliconi topology, the switches S1 and S4 are closed in phase 1, where C2 is charged by Vn, but C1 is lifted by Vn, creating a direct AC path through C1. And then in phase 2, the switches S2 and S3 are closed, creating a direct AC path through C2. So in both phases of the Pelliconi topology, there's a direct AC path, whereas for the Doppler topology, it was only in one phase. Designing the Doppler topology and the Pelliconi topology to have the same equivalent output resistance, the flying capacitor of the Doppler topology must be equal to the sum of the C1 and C2 of the Pelliconi topology. And having the same C out, the capacitor voltage division in the Doppler topology, the AC signal from V in to V out will be attenuated less than it would be for the Pelliconi topology. This is also illustrated by the simulation waveforms down here, where for the Doppler topology, the AC signal on the supply is only present on the output half of the time. Whereas for the Pelliconi topology, the amplitude of the AC signal is half because of the voltage division, capacitor voltage division being more, the attenuation from the voltage division is higher. And if you evaluate the power supply rejection as the peak-to-peak value on the output, Doppler topology performs worse than the Pelliconi topology. It's also possible to implement the Doppler without an AC path. In this case, it's a two-stage voltage Doppler, where the same implementation with different clocking schemes can change the AC paths. So for the top one in phase B, there's a path through C1 and C3 to the output. So that's a direct AC path from V in to V out. Whereas for the one down here in phase B, there's an AC path through C1 through to here, where C2 and C3 is charged by it. Nothing else happens. And in phase A, starting from the output, it goes through C3 to C2. So there's no direct path in any of the two phases from V in to V out. So direct AC paths has been eliminated by clocking the topology differently. This can also be seen in waveforms, where the Doppler with the AC path has a larger peak-to-peak value compared to the Doppler without the AC path, and evaluated the power supply rejection ratio versus frequency. There's a low frequency power supply rejection ratio of -12 dB due to a converter gain of 4. But as the frequency goes up of the sine wave on the input, the power supply rejection kicks in, and then the Doppler with the AC path has a roll-off in power supply rejection before the Doppler without an AC path due to the presence of an AC path. So just by clogging a topology differently, it's possible to achieve approximately 6 dB more of power supply rejection in this frequency range. In addition to the topology-dependent AC paths, there's also topology-dependent sampling rates, which is relevant as switch capacitor converters are sampling circuits, so they have a sampling rate, and if the signals on the supply has a frequency above the Nyquist frequency of a switch cap converter, then the signals will be aliased into lower frequencies, which will affect the power supply rejection at the high frequencies. In the Pelliconi topology, the supply is sampled on both clock phases, and as such, the sampling rate is twice the clock frequency because it's sampled on the rising and falling edge of the clock, and hence the Nyquist frequency of the Pelliconi topology is equal to the clock frequency. On the right, we have a heap topology where the supply is only sampled in one phase, so it's only sampled on one edge of the clock, and as such, the Nyquist frequency is half the clock frequency. And will be shown later how this affects the power supply rejection. It is possible to increase the sampling rate by increasing the switching frequency, but then to maintain an equivalent R out, the capacitors must be reduced in size accordingly, and switching a converter faster leads to more switching losses. To compare 4 topologies to illustrate the impact of direct AC paths and sampling rates, these 4 topologies have been implemented for a biasing application where the load is a 10 picofarad capacitance with a 100 gigohm resistance in parallel that represent the leakage of the MEMS sensor. the topologies have been designed to have an equivalent output resistance of 50 megaohms, and the switching frequency is 100 kilohertz. And the effective low pass minus 3 dB frequency is 318 hertz, and A and B are nano 11 clock signals. So we have the single heap topology presented before that has half the sample rate of the clock frequency, a sample rate equal to the clock frequency, but a Nyquist rate of half the clock frequency. Then there's a parallel heap where it's two heaps connected in parallel with half the capacitor size, but one lane is clocked BBAA and the other is clocked AABB, and this effectively doubles the sample rate of the converter, giving it a Nyquist frequency equal to the clock frequency. Now we have the Doppler topology and the Pelliconi topology from before. So the simulated power supply rejection and the implication of AC paths is presented for the Pelliconi, the Doppler, and the parallel heap, where the parallel heap has no AC path. At first, we have a power supply rejection ratio of minus 6 dB due to the voltage gain of 2 of each converter. And then at around 300 hertz, we have the minus 3 dB frequency. And then as we go up in frequency, the first one to have diminishing performance is the Doppler topology due to the larger impact of AC paths in that one, because it has larger flying capacitor. Next, we have the Pelliconi, which achieves a better power supply rejection ratio, but the one with the best performance is the parallel heap because there's no AC paths. Looking at the effect of aliasing, as the converters, they start at minus 6 dB and go up in power supply rejection ratio, then at the Nyquist frequency of the parallel heap, the Pelliconi and the Doppler, the power supply rejection begins to diminish until it hits twice the Nyquist frequency, and the signals alias down into low frequency signals, and down into lower frequencies, and the power supply rejection falls to minus 6 dB again. The single heap that has half the sampling rate of the other topologies already see a diminishing power supply rejection ratio at 50 kilohertz, and at 100 kilohertz, the power supply rejection is gone. So just based on topology, the single heap has a worse frequency performance due to aliasing. The shown examples so far have focused on the biasing applications where a large output resistance of the converter is acceptable, but in power applications where a significant amount of watts have to be converted by the switch cap converter, designers usually try to minimize the output resistance to maximize the efficiency of the converter, but minimizing the output resistance maximizes the minus 3 dB frequency of the low pass filter. For example, given a voltage Doppler switch at 100 kilohertz with an ideal voltage gain of 2 volts per volt, as shown in previous examples, but now it has to supply 9 volts to a 900 kilo ohm load from a 5 volt supply, the output resistance must be 100 kilo ohm, and with an output capacity of 10 picofarads, the minus 3 dB frequency would be 160 hertz, which is higher than the Nyquist frequency of the converter. So aliasing effectively eliminate any inherent PSR in this example. And to achieve the same minus 3 dB frequency as in the biasing application, the output capacitor would have to be increased to a much larger capacitor, which might not be feasible in an integrated circuit. So in conclusion, for power applications, it can be expensive to implement anything that can use this inherent power supply rejection in switch capacitor converters. In conclusion, switch cap converters have an inherent power supply rejection, which may be sufficient to relax requirements to adjacent circuits. An inherent power supply rejection of more than 40 dB was observed in simulations for biasing applications. And if the 40 dB is in the right frequency range, the LDO might be relaxed significantly, like the LDO specifications. Furthermore, the inherent power supply rejection is limited by topology-dependent AC paths and sampling rates, even though the converter specifications are the same. So designers would need to consider which topology they're using, how they're clocking it, and how they design it in terms of switching frequency and capacitor sizes. And as shown with the publication, inherent power supply rejection may not always be feasible to design for. So, yeah.
Thank you for your very energetic presentation. Maybe somebody would like to ask a question according to this paper, to this presentation. If not, maybe I will ask you a question. For what kind of application we can use such kind of converters? This is the one question. And if you can just switch your presentation into the picture, maybe second, maybe third one.
Yeah, personally I work with the map sensors applications.
Next one. Yeah, another one. No, next. Oh, no, last one.
This one.
One more up.
Oh,
here. What's the ground on the third one?
Oh, that's it's just have been removed. It's a floating ground, I guess you could say that. It's the one that was here.
Okay. So application. Say something about
application. I work with map sensors, and more specifically work with maps microphones. Where you're interested in low noise in the 20 to 20 kilohertz frequency range. So you try to remove any noise in that area, and then you have this thing called A weighting, which is basically a high pass and low pass filter, a baseband filter around 1 kilohertz. So the specifications for LDOs and filters are based on minimizing the noise around 1 to 10 kilohertz. And if the switch cap converter can provide a power supply rejection of say 20 dB in that frequency range, then the specifications for the LDO and the filter might be relaxed, which means that you can get reduce filter capacitance by a factor of 2 to 10, perhaps, dependent on the inherent power supply rejection of the switch cap converter. And it's not something people have looked into before based on what you could find in literature. Of course, it's included in simulations when people simulate these kind of circuits, but it has not been considered during the design process before.
Okay, thank you. We have to switch to another presentation. The presenter is Luís Carlos Gomes André from Portugal. Thank you very much for your presentation. Yeah.
Welcome.
The next one, because time is going, is textile antenna for first-person view goggles. Luís.
Yes. Hello.
Okay, you can you start your presentation?
I think
11 minutes, maybe up to 12 minutes of presentation, and next we will discuss something. Okay, please start.
Okay, so I'm Luís André, and I will be presenting the paper Textile Antenna for First-Person View Goggles. First, I'll show you the outline of the work. Firstly, we'll start with an introduction about UAVs and first-person view. Then we'll talk about a bit about textile antennas. Then the antenna design, the results, and we'll compare our antenna to a commercial antenna widely used in order to verify results. So, firstly, I'll start with a small introduction explaining the FPV system. Unmanned aerial vehicles, known as UAVs, also known as drones, are aerial vehicles that can be controlled remotely and don't require a crew on board. With increasing demand and interest in drones, the first-person view technology appears. This technology is a method used to pilot the drone that allows the pilot to have a more useful perspective as if he was inside the aircraft, thus making it possible to obtain better control and a more useful perspective for the pilot. This technology opens possibilities in several areas, from agriculture to rescue missions. Despite the numerous applications, the most explored areas are surveillance and FPV drone racing. Here we can see a complete FPV system. It's basically composed of 3 elements: a radio controller, used to control the drone itself, and the FPV goggles that have many ways to be mounted, but usually they have two antennas, omnidirectional one and a directional antenna with high gain. This paper will focus on the design of the directional antenna. So currently, these antennas, the high gain antennas, currently use a rigid substrate as FR4 and can be large and heavy. As you can see here from the picture, this is a widely used antenna. It's the low-cost triple-feed patch antenna by Martin Baert. It's widely used, and as you can see, it's very large, difficult to wear, and quite heavy, as it hangs from the goggles, making it very hard to use and to wear. So, what are textile antennas? Textile antennas are antennas made out of textile materials. And to develop this type of antenna, the knowledge of the properties of the textile material is crucial, as well as the knowledge of the manufacturing processes. The properties of the textile materials can influence the behavior of the antenna, thus making textile antennas require the characterization of the material in order to be successfully designed. For the antenna construction, it's used a specifically conductive material, and for the substrate, we can use ordinary textile materials as long as they are very well characterized for the frequency in use. Here we'll talk about the antenna design. So, in order for the antenna to work in the FPV range, there are a few standards that it has to follow. For example, the FPV transmission range are from 6.645 GHz to 5.945 GHz. The central frequency is 5.795, near 5.8 GHz. And these antennas usually have a gain between 9 and 12 dBi. And in order to achieve this gain, we will use a 2x2 antenna array. These antennas can have linear or circular polarization, but for this work we will use circular, and we'll use right-hand circular polarization in order to achieve a greater signal reception. So, the design considerations. For the dielectric substrate, it was used PDA black, which is a tight-knit polyester wrap material. And for the conductive parts, we'll use pure copper polyester taffeta fabric. In the design, to achieve circular polarization, we'll use a squared patch with chamfered edges, as we can see in the picture. For the design feeding network, in this design, the feeding network impedance of the radiation patch has to be taken into consideration to ensure proper impedance matching. The width of the lines is also taken into consideration, as this should be as narrow to avoid parasitic effects, but keeping in mind the construction limits. Firstly, a 7-ohm line was connects both the patches horizontally. We can see it's named L1 and L2. Then 2 quarter wavelength transformers are defined as L3, connect to the central line. This central line, L4, is 100 ohm lines that connects the upper and the lower part. In the middle of this line, it's a 50 ohm line where the SMA connection will be attached. The spacing between each radiating patch is 3/4 of a lambda. This separation allows a trade-off between optimal antenna parameters such as gain, half-power beam width, and side lobe level. Here we can see the manufactured antenna. And for the results, the simulated and the manufactured antenna have pretty similar results, having the simulated antenna an S11 at the central frequency of -38, and the manufactured antenna as S11 at the frequency of interest of -17. The bandwidth of the simulated antenna is above 1 GHz, so is the manufactured antenna. For the gain, the manufactured antenna has a slightly lower gain, having 6 dB, and the constructed, and sorry, there's a mistake here. Here in the simulated, it's the other way around. But the simulated antenna has a 9 dB, and the constructed antenna has the 6 dB. The F-power beamwidth is pretty similar, having the constructed antenna 40 and the simulated 36. Here we are comparing our antenna to the commercial antenna, the Martha Bayard antenna. As we can see, the central frequency is about the same. The bandwidth is actually the same. The S11 at the central frequency is pretty similar. The antenna gain is where our antenna diverges from the other antenna. Ours having the 6 dBi and the commercial having the 9.3 dBi. The half-power beamwidth is also similar. Our is a little bit narrower. Here we have a physical comparison where we can see the commercial antenna, that the commercial antenna has a very it's very large when compared to ours. Our antenna stays close to the goggles, making it very easy to wear. It's a lot has a lot of less weight, and the size is pretty small also. So in conclusion, a solution to the current problem with portability and comfort of the FPV antennas was presented using a textile antenna. This comparison between the design and the commercial antenna shows promising results, and the footprint of the antenna of the design antenna was reduced successfully. Thank you. I don't know if anyone has any questions.
Okay, thank you very much for your presentation. Maybe somebody would like to ask a question. We are waiting for questions. If not, I will ask you a question. Did you test your antenna under the deformation process? Because you know it's a very important thing.
With a drone?
You know, with your antenna, which is placed on the somebody's.
So we tested it like this. Tested here. No, it wasn't tested on the goggles. It was tested on a foam surface.
Yes.
It was not tested here. Even though we, as we can see here, it's a bit bended. That's because we had no way to put it correctly. But ideally, it will have a stabilization platform under it for it to sit straight.
Okay, thank you very much. Now we can start. We can start next presentation, which will be presented by Professor Lubomir Valieriev Bogdanov from Bulgaria. Yeah. The presentation will be about the Dallos framework for high-level synthesis, past, present, and future. Can you start?
Yes.
Okay.
Mr. Chairman, I'll start my presentation with a brief introduction about the problem and about development of embedded systems. Then I'll show you an implementation that is open source and can be freely downloaded from the internet. Then I'll conclude my presentation with an example. As we are all aware of, embedded system design has taken a vast course in the past years in the development, and different stages of development have been used throughout the years. As we know, back in the days, the circuits were developed on a transistor level, where you would use your transistors to make up the circuitry. and of course the designs weren't that complex. So the next level of abstraction is to group those transistors into logic gates, and then people were using logic gates for development. The gates were grouped together to have to form more complex digital circuits, such as arithmetic logic units, multiply units, shifters, bit shifters, register blocks, and so on. And those type of development is, we call it the processor level development. And currently, the highest level of abstraction that we could use is to have a system level development, when all the functional units that I have mentioned previously are grouped together, and we actually use processors, hardware accelerators, buses, and memories. So all of the levels of abstraction are important, and they will exist together forever. But we want to focus now on the area that is a little less developed during the years. So now the trend is to make systems, to make system level design. As we know, such systems or integrated development environments exist commercially, but we want to propose now an open source alternative. And by the way, I teach my students that one engineer can tell the level of abstraction by the elements from the library that he or she is using. So as you can see here, the library is transistor, here of logic gates, here of functional units, and here of processors and acceleration units. Okay, so three professors, or actually two professors and a PhD student were involved in the making of such an environment. These are Professor Ed Depreter and Todor Stefanov from Leiden University in the Netherlands, and Chris Tunikov, who was the PhD student that successfully defended his PhD. In 2009, there was a foundation that was started, and it's called Daedalus, that is named after the system level tools used to design embedded systems. The Daedalus tool includes many tools, all of which that require that you start with a sequential C program that actually describes the behavior of your application. So it is very important here to note that the program is sequential. So there is no parallel programming, just to make things easier for the developer. And then this sequential program is taken as an input to a tool called PNGen that actually produces a parallel specification in XML version that describes that same application, but with parallel processes. So here the process of parallelizing a program has been automated. But this is not enough by itself to make a system. You would also need a platform specification that actually is also an XML description that defines the components in your system, and you would also require a mapping specification that shows the connection between each hardware element and each process in your application specification. Those three XML files are passed to the ESPAM development environment, and ESPAM generates RTL description of our system. This RTL description could be taken to some standard tools that many such exist, like for example the Xilinx Platform Studio and the Xilinx Software Development Kit. For optimization of the design, colleagues from Amsterdam University developed Sesame that aims to find the perfect mapping between the hardware and the software. The PNGN tool, here is one example of using this tool. You write your sequential C program. It has to comply with some standards, but those standards aren't grammatical, but they are logical. So if you obey them, you can produce your parallel specification. And about the hardware that is produced by ESPAM, as you can see, we can have a few elements such as microprocessors, communication memories, local memories. And each microprocessor communicates with the other through the communication memory. Of course, the ESPAM tool takes many steps to produce such system. I won't go into detail about them. And one example of producing a streaming application that is produced by Daedalus is, for example, the JPEG encoder. And as you can see, here we have a graph that shows different implementations. All the dots are different implementations. And here we have the speed of each design. And here we have the memory that is taken, actually the logical units that are taken on the FPGA. So you can select whichever design you like that best suits your performance. You can select between heterogeneous or homogeneous embedded systems. You're free to download this tool. If you have any problems, you can always, with the installation, you can always email me and I'll write to the colleagues from the Netherlands. And thank you for your attention.
Thank you very much for your presentation. We are waiting for questions, maybe. If not, I would like to ask you just a simple question. Is it free for didactic purpose or just for commercial too? You can use it free for commercial?
Yes, it is free for commercial as well as open source designs.
Okay, thank you very much. Very nice. Okay, now we have to start new presentation. We are waiting for Ben Yusu from China. Are you here? Yeah. Ben Yusu will present a case study of direct current resistivity method for disaster water source detection in coal mining. The presentation, I think, will be very interesting. So, please start. Waiting for you. Please share the screen. Yes, yes. Okay. Now we can see your presentation. The floor is yours. We cannot hear you. Ben Yusu, turn on your microphone. We cannot hear you. Microphone, then. We have some technical issues. Oh, we can hear you right now. Please share your screen. No problem.
Waiting me from mute. Okay.
Just please share your screen.
Okay. What's this?
Easy, easy, easy. We can wait for a while.
Maybe not.
We have time. Oh, we can see right now your presentation.
You can you hear?
We can hear you, yes.
Okay, thank you very much.
Maybe you can
Good
press
morning.
Full screen mode or presentation mode, just for full screen.
Oh, yes, this is for.
It's because we can see only the PowerPoint screen, not.
You cannot see PowerPoint.
We cannot see your full screen mode.
How about this?
No,
no.
No.
Oh, sorry.
Not a problem. Okay, let it be. Let it be. Just start your presentation because time is going.
Okay. I'm sorry. Hi everyone. This is Ben Yusuf from Department of Geophysics, China University of Money and Technology. Today I will interpret my work about a case study of direct current resistivity method for disaster water source detection in coal mining. The outline of my research totally have 3 parts. The first one is the purpose of my research. The second one is the main content of my research, and then is the conclusion. There are many reasons result in coal mining disaster, such as rock burst, roadway deformation, and even instability damage in the coal mine tunnel. But my research is about inrush of the water and mud, especially inrush of the water. Because in the coal mining, the pressure is very high, so if once the underground water is conducted into the coal mine tunnel, it will flood the coal mine tunnel immediately, and it will cause lives lost, and many workers will have to stop it. It costs a lot of lot of losses. So we try to use the geophysical method to explore the source of the water. And here is my research area. The research area is located in the northwest of China. Basically, this area, the climate is very dry, but underground water is quite abundant, especially below 200 meters from ground surface, and it will bring a greater threat to the coal mining. So my research is using a geophysical method to detect geological information below the coal seam. As shown in the figure, the force have been explored in the coal seam. So it is very dangerous if the water conduct into the coal seam by the force. Hence, we have to explore whether there is water in the flow or not by direct current resistivity method. Because this is the workface, because the workface is so large. For this work, we separated the whole workface into two parts, and we have to use a method to, like this, detect the force or the water source. As mentioned above, we separate the whole workface into two parts. For the first pass, we use 160 electrodes to collect data, and for another one, we used 165 electrodes to collect the data. And for my research work, first we will do some numerical simulation, and they are forward modeling and inverse modeling. For the forward modeling, we solve these equations, and then to get the voltage is phi. And for the reverse, we should construct the function, and finally we will get the geological resistivity information by solving the least square, but here I will do not interpret it. In order to verify the correctness of the algorithm, we compared with analytical solution and numeric solution by uniform Earth medium. The line marked with circle is numerical simulation. And the line marked with triangle is analytic solution. So we can see they matched very well. It shows that my code is right. And for the verifies of the inversion, we do comparison between geophysical model and inversion result. So we can see they can match very well. And this figure shows my field work. This is underground surface about 300 meters from the coal mining to the ground surface. And as mentioned, we separated the whole workface into two parts, and this is part one, and this is part two. So in order to get the information from of the coal seam, we use this equipments. This equipments because in the coal mine tunnel usually there is a gas. It is easy explored if there is a far flat. Hence, we have to ensure the safety. and also our administration has a very strict standard for equipment. So this equipment is a special design for the coal mine, and because in the coal mine tunnel and the environment is very bad, so we have to efficiently to collect the data. Also, we use low current and low current to get the data. This is part one. We get the data from the equipment, and from the equipment we get two information. First is current, and second is voltage. Because we will use this to invert to get resistivity information of the foresee, and this is part two, and also this is the current, this is the voltage, and based on above information get from the equipment, we will do the inversion to get the information of the coal seam flow, and this is part one. From those information, this is the current, this is the voltage. We will calculate the resistivity distribution of the earth, and because we use the method we can calculate the distribution of the resistivity in 3D data volume, so we can get any information if we use the slash like this. This is a slash. We can cut a slash from the volume, so we can clearly see the distribution of the resistivity. And this information is very useful for geologists to get information about geology, and they will understand the hydrogeology. And this is part two. This is information, and also we use the inverse method to get the volume of the 3D data resistivity volume. And also we can cut a slash from the volume, and then we will get the information of the Earth. So next is my conclusions. First is the resistivity distribution of the coal seam flow can be obtained by direct current resistivity measure, and this will provide useful information for hydrogeologists to understand the hydrogeology. The second, generally speaking, algorithm of the forward and inverse is a half space. A half space like we put the electrode on the ground surface. But in fact, the field work is really in the whole space because we work in the underground. So in the future, we will process data about the whole space theory in the future. Okay, thank you very much. I'm sorry, not display my slides very good. And this is to figure. This is I published to US in the command, and this is my worker after work in the command. Thank you very much.
Thank you very much for your very nice presentation. Maybe somebody would like to ask a question for a presenter. I cannot see. Maybe I would like to ask you a question. You have presented a measurement system over the, I don't know what the slide was. Did you build the measurement system your own, or it's just bought? Measurement system.
Master?
Yeah, can you hear me?
Yeah, I can see you.
Did you build the measurement system your own? Measurements.
He's asking if you have set up the system of the experiment yourself.
Yeah.
Yeah, I measure the data in the command. Sorry.
Okay. Okay. So maybe we will talk about it after the session. Now it's time to start new one presentation. Yes.
Okay.
We will ask Professor Nima Georgi from Ireland to present Fermi level tuning. Yes. Can you?
Okay, thank you.
Us?
So
Yeah.
give a second so I can share my screen.
Fermi level, yes, tuning by nanograding depth in silicon substrates.
Yeah, thank you very much. So, so this is, do you see my screen now?
Yes, we can see your screen, but if you can just switch to the full screen.
What about now?
Yes,
Yeah,
presentation. Yes,
yeah,
very good.
So thank you very much and good morning to everyone. I hope it is not, or good afternoon to anyone who is out of Europe. So what we have presented here is about silicon solar cell or silicon devices, not especially on solar cell, but it can be any devices. The technique that we have generated is nanograting. I'm working with Professor Tavkelidze and my Georgian colleagues. We are doing collaboration. I'm myself based in Ireland. So what we have presented here is developing a relatively new method to produce p-n junctions or kind of optoelectronic devices, which could be a new architecture. What we use is a very simple method, is in fact a laser interferometry lithography. And we aim to create a p-n junction or electric field just by creating nano-sized indents on the surface of the silicon substrates. I need to go a little bit into the physics of these devices. So nanograting is a method which externally dopes the surface of the silicon. We call it G-doping or geometry doping as well. Normally, you need two layers to come together in order to create p-n junction and produce electric field where this can collect the electrons and create a current in a solar cell, for example, or in a p-n junction device. But here we are using just periodical nano indents on the surface. As you see, the size of A, let me also check what is the, if I get my annotation here, all right. Maybe this one there, yeah. So bring it here. So you see that we have created very small size of indents on the surface of the silicon. So this is, for example, a silicon substrate. It can be a p-type or an n-type, and then we just create a very a small size patterning. We call it nanograting. So when you see NG, in fact, I refer to these indents. And the size of these indents could be 20 nanometer, 30 nanometer, and it is a periodical. So we are making this with lithography methods. A little bit about this impact of this nanograting on the surface. So what we get is very small or lower density of states for this layer. So if there is a plane layer and you have a nanograded layer on the surface, you will get, in fact, less density of states. So when we get a less density of state, it means that the electrons, in fact, will get less probability to or capability to stay on the valence band, and then they have to jump to the conduction band. So we have a lot of electrons here, which means that this layer will show very higher conductivity. A higher conductivity, in fact, means that the electrical behavior of this layer is changing. So in fact, if we have a p-type silicon substrate, we will then have an n-type surface. So here you can say this is a p-type, but then when we graded the surface, this will show a n-type. Yeah. So then we will have a p-n junction. So this will become a p-n junction, and we expect that this will collect the carriers by the electric field. So this is the point of physics behind that. So the quantum states on the valence band reduce, or the probability of electrons staying here is reduced and minimized, and then the electrons have to jump to the conduction band, and this in fact increases the conductivity of this layer. Let me go maybe to the next. I have to clear all the drawings. So maybe people would like to ask about the experimental or lithography methods. The system is very simple, I think. We just use ultraviolet interference lithography, and then it comes to, we, for example, use usually 266 nanometer if you could use it, or sometimes, or we use 363 nanometer. So the power is 1 watt or half a watt, and then we expose it to the surface of the silicon, and we create patterns by the nanosize. So depths of the nanosize and indents could be 20 to 30 nanometer, or until 40 nanometer, and the periodicity is like 100 to 150 micrometer. So in fact, we created periodical patterns. You see in the SEM image here that we are, these are the indents. Sorry, here the black ones. So the periodicity is very good. We have used SEM imaging to show if this really is happening and what is the preciseness of the geometry. So when we use very cheap laser and very precise patterning, in fact, we are showing the quality of our experiments. So what remains here is to test different substrates with this patterning. So we are using p-type silicon substrate, or with different resistivity on the surface. So P+ type, which means the higher doping and less resistivity, and then we can also use N+ type silicon substrate. So different silicon substrates, if we expose them to this nanograting, then the nanograting itself will also show a different conductivity. So for example, if you use N+ here, you will expect maybe N or P or even I inherent properties at the surface. So the system, the way we make it is in a way that we can compare it with a plain silicon surface. So for example, imagine here would be an N+ type and nanograting, and here it would be a reference cell, for example, so we can compare the results when we characterize them. So we want to show if nanograting is increasing the electrical properties or showing any p-n junction behavior, and we are comparing that with the plain silicon surface where there is no grating. Then the chip, the size of the chips is small. We are hoping to increase that by using a better laser, like 10 millimeter at the moment. But we can, in fact, on this very small surface, we can create like groups or categorized groups of nanograting. We can change the size of this grating. We can change these widths. We can change the conductivity or a better geometry. So we have the thickness, we have the widths, and we have the depths. So why we are writing here lambda/4 is because we want the depths of the nanograting to be comparable with the de Broglie's wavelengths of the electrons. Again, I'm showing a simple lithography setup. It comes also with a reactive ion etching on the surface, and then different size of the laser and what widths we could get from that on nanograting. So maybe some results again on so AFM or topography images. We want to ensure if the nanograting is done perfectly. So this SEM images is showing good. On the other side, we have AFM images, which are showing a high quality. This little bit I increased the image, but it's almost clear that it is happening. So the grading and the depths. I think with a better laser, we can even improve this and remove some noises from the experiments. I have done some surface composition measurements on that. It's going a little bit onto the material investigation. So when we have a silicon, we expect to get a lot of silicon peaks. There are always carbon and oxygen on the surface because we have done this in, we handle the samples in air ambient, so there is a lot of oxygen. So the peak of oxygen is high and the carbon is there because the nanograting sample was staged on the carbon pad. So we also receive a lot of carbon there, but this is normal for the XP experiments. So we see that silicon with at different shells of silicon is happening on around 100 and then 150. So we ensure that on the surface there is no defect complexes. So for example, there you don't expect to see different materials which could act as a defect on the surface and impose any electrical noises into the carrier transport or impede the electrons from the at the junction. So then we tried with the Kelvin probe measurements and we measured the Fermi level difference of these junctions. So we have a, let me maybe draw a little bit better and make it clear. So for example, you have a band diagram here, and then you want to see the difference in between the energy levels. So for example, here is the Fermi level of the EFN, and then here is the EF. So we actually measured this distance. So we measured different samples, about 32 samples, in order to get a good understanding on that. So you see the range of the difference in the Fermi level is less than 0.4 electron volt. So this is very acceptable, I think, because in normal PN junctions we also have it less than half electron volt. So most samples are in this range, and the mean difference is very small, so it is acceptable level. And then we also measured that on a p-type substrate. So, or sorry, here is n-type, should be n-type substrate. We see again the in fact for this silicon, n-type silicon, we have a better coherence between the results. So we measured on 32 samples, and the difference is the Fermi level difference is in fact between 0.15 and 3. So this is very good. I mean, it seems that n-type silicon shows a better compatibility with this method. So the average of this difference was measured for different samples. We have a p-type sample, which seems to be also the most popular silicon substrate that we use. So for a bigger depth, we see more coherence between the results. So most samples show around 0.02 to 0.04 electron volt difference on the Fermi level for different sizes. So in fact, we wanted to investigate if we increase the depths of the nanograting, will we get different Fermi level difference at the surface or not? So we see that, yes, in fact, for p-type substrate, when we increase the depths of the nanograting, we get less differences. So this can show, in fact, that nanograting can tune the Fermi level on the surface. So in fact, if you want to make a p-n junction which has a very wide Fermi level between the p-type and the p+ type, for example, you will need to reduce the depth of the nanograting to 10 nanometer, and this you can do with a better laser, with suitable laser or lithography method. And then when you want to reduce this difference, which means what I'm saying is, in fact, the band diagrams, if anybody knows the band diagrams, will understand that this Fermi level is very important thing for us in order to get more carriers collected. So these are the electrons and these are the holes, and this is the Fermi level. So we are tuning this level, in fact. So this is the p-type silicon, and this is the nanograting level here. So if we want to get much better conductivity or electron carrier transport, we will reduce this, or we will increase this, so the potential becomes higher, and then we will have a better carrier transport. So in fact, we have to use smaller nano depths, nanograting depths. So in this case, we have to use maybe a more advanced method or laser. And then if we want just more plain difference, we get a higher depth of nanograting. So this is in fact a very unique result. I believe that my colleague Arthur has extracted this, and it is indicative of how we can tune the level of this the carrier transport. So we can actually control the carrier transport by these nano depths. Okay, so this was my presentation. I hope this was interesting, and if there is any question, I can be hopefully I can answer the question. My colleague Afto is here as well, and I hope he will be happy with my presentation and also participate here. Thank you.
Thank you for your presentation. Very nice. Now we are asking you maybe about some questions from our audience. We are waiting.
Maybe I have one question.
Okay, go. Please go.
How you ensure the stable number of dopants? What kind of technology you use?
So here, that's the point. We buy usually the wafers, sample silicon wafers from commercial providers. But the point is that we do not use doping here. If you want to use any doping, I think we use boron. So by chemical processing. But then the point here is that we don't want the nanograting, the surface to be doped with impurities. So that's why we are using, in fact, a geometry-based doping. So if there was a dop,
you try to avoid some problems, yes.
Yeah, so that's the point. Yeah. So for example, for gallium nitride, you would like to have a method, external method like doping without using the chemicals or interfering into the material. So I think this would be great thing. Here, there was a dop that we cannot get a p-n junction, or there is maybe defect on the surface which is showing some p-n junction behavior, but the temperature measurements, which I haven't shown here, it in fact shows that these grating, because of the physical quantum physics constraints which brings on the surface, it can show, it can change the conductivity of the surface to, for example, another way. Like if there is a p-type substrate, it can show n-type behavior. So this is not you. In fact, we are not going to use the external impurity doping, but by just bringing geometry into on board. Yeah. Thank you.
Okay.
Thank you. I have maybe somebody would like to ask a question. No. I just have one remark maybe about your article, not exactly presentation. Could you switch to 2 slides, 3 slides down? Yeah.
Maybe 3 here.
Bottom right side, we can see the microscope, yes, picture. It would be nice to place such a picture to your article in order to explain what kind of shape we can observe. Yes, because
I think we have shown. Yeah, I think we have shown this one into.
Yes, this one. Yes, but
so we are trying to get. So this one maybe belong to another substrate, so it is not very correlated. But in the future, we are going to.
But would be nice to to place the second one picture from the bottom.
Yeah.
B, to explain what exactly we can see in the picture on the
in fact
side,
I have made it schematically here, but not showing the AFM results. So yeah, in fact, if we get more access to the AFM topography system, we can definitely add more results.
Yeah. So thank you very much.
You're very welcome. My pleasure. And I hope if there is any collaboration, we would be happy to do. Thank you so much.
Thank you very much. Now we will switch to the next presentation by Professor Yakin Sabah Mezal from Iraq. Yeah, miniaturize a microstrip duplexer based on FR4 substrate. If you can just start your presentation, share your screen for us.
Hi, everybody. I hope my presentation is appeared now. Is it okay? You see that
we can see, but if you can just turn your presentation, yes, in the slideshow.
Now, is it clear?
Oh yes, that's good.
Okay. Hi, everybody. I am Dr. Yakin Sabah Mizal from Kaunas University College. I am the Director of Scientific Affairs Department at this university. My paper is about miniaturized microstrip duplexer based on FR4 substrate. Duplexer stands for passive circuit that can be used to separate the frequency band from wide band. It can be used in radio transmission, satellite communication, and whatever, based on band frequencies. Here we have manufacturers and successfully tested this duplexer based on 2 channels. Duplexer here is made from FR substrate, which is very cost effective. Now, the aim of this work is as follows: compact size, very compact, promising isolation values, better than 31 decibel, flexibility in design, very easy in fabrication, and low profile. Now, the main items or main components of my duplexer design is the step impedance resonator and uniform impedance resonator. But step impedance resonator are the most component in my design. Step impedance resonator stands for resonant component that operates either in TIM or quasi-TIM mode. It consists of the normal SIR consists of 2 sections. The lower width represent higher impedance, and the higher width represent lower impedance, and the lower width represent higher impedance. Namely Z1 and Z2. Theta1 and Theta2 represent electrical length. Here, the ABCD matrices will be the same with the lower physical SIR based on this matrix formula. Now, the most important issue with the step impedance resonator is impedance ratio. Impedance ratio I need with Z2 over Z1. As you see, as I told you, the Z2 represent lower impedance and Z1 represent higher impedance. So it can be calculated as well by this formula, tan theta1 multiplied by tan theta2. Theta1 and theta2, as I explained before, they are represent the electrical length. Here represent multiple mode and can be used in to design filters, duplexer, triplexers for dual or multiple bands. So I used this SIR concept in my design. But what is the new issues in my design? Here in my design, I combined SIR, Mender line resonators, and uniform impedance resonator to get something. These things I will explain them later. are based on compactness, higher isolation, and frequency band preferred in a wireless communication system. What about Mendel-line resonator? Mendel-line resonator represent planar layout that can be fabricated easily. This is the Mendel-line resonator layout, and they represent long element circuit, passive circuits. The impedance of LC series can computed by this formula. And the phase delay can computed by this formula, can inverse the omega L minus 1 over omega C over all over R load. The Mendel-line phase can be determined by 2 pi over lambda I. Here, the design of microstrip duplexer, which is represent the upper layer of the microstrip duplexer. Now, the overall size, as well in the title of my paper, it is very compact. Its compactness is about 32 by 26 millimeters square. That means it is about 33 centimeter by 2.6 centimeters square. Material, the used material, as I explained before, is FR4, which is very effective, and it is available everywhere. Director constant is about 4.3, and director thickness is about 1.5. Loss tangent is about 0.02. I use the software Applied Wave Research, which is a variation of microwave office to simulate them. And I successfully manufactured it by VNA measurement. Operating frequency, the channels are 1.8 to 2.5 gigahertz. This is the design before assemblation. These are represent SIR components. This is port 2 SIR, port 1 SIR, port 3 SIR. These are uniform impedance resonator, highlighted by red color. And this is Mendel-line resonator. So my design in the upper layer or in the microstrip the structure has these components: SIR component, UIR component, and Mendel-line resonator. I combined them and I got this structure. These will be operate at duplexer for dual channels. I simulated it and get this simulation results, scattering parameters. As you see, we have two bands. The first band about 1.8, the second band about 2.5 gigahertz, which are interesting for modern wireless application. And we have isolation. As you see, isolation is better one, 31 decibel, which is very preferred in duplexer design. These are the details of the channels. For first channel, the frequency band 1.855. Insertion loss is about 4.2. Return loss is 32. Bandwidth 1.82 to 1.88. The second channel 2.505. Insertion loss is about 3.3 decibel. Return loss is 31. Bandwidth 2.451 to 2.56. As you see, the frequency band are very narrow, which is very useful to prevent interference and communication signals. in which there are interference. Also, you can see the isolation is better than 31 decibel. Here, I made the simulation by sonnets to investigate the effective area of Resonator. As you see, at 1.855 gigahertz, the high scalar, namely magnetic intensity, are concentrated in these regions, in the underlying resonator and the left side, which that stand for these filters, because the Lexar represent here two filters, the combined one port that represent this filter operate at 1.855 gigahertz. On the other hand, this resonator in the second filter operates in 2.505 gigahertz. So the most important effective area are in the underlying resonator. As you see, and by them we can modify the structure accordingly to increase or decrease the design frequency. So, what about the group delay? Here, as you will see, the group delay at the design frequency are 46.1 at the first band, and minus 35.6 for the second band. All of them are very low and reasonable for my design. I actually compared my design with other reported design in the literature, and I got these results. Mostly, as you see, my design has more compactness as compared to other, and has very competitive resolution, as you see, by 31 decibel. But the disadvantage is the insertion loss, and I discussed this in the paper. It is a little of a problem and can be solved easily. This is my manufacturer design, and this is the coin of Turkish lira. I tested it by vector network analyzer of version HP M9923A. As you see, now it is very compact and can be integrated with many wireless systems, operated at 1.8 and 2.5 gigahertz. These are my measurements. There are good to reliable agreement between simulation and measurement. But the most important thing is the isolation, which aimed to be better than 31. As you see, there is good agreement between all of them. The main differences between simulation and measurement are due to SMA soldering, maybe lab environment, and coaxial cable setup. So we use dual band bandpass filters to design the Lexar, namely to separate operated band to 1.855 and 2.505 gigahertz band. Every filter has constructed underlying resonator uniform SIR and uniform impedance resonator. And the compactness of this filter, of this the Lexar is 32 by 226 millimeters squared, which are visible and incorporated with many wireless configuration. Thank you for your attention. Any question, please?
Thank you very much for your presentation. Maybe somebody would like to ask a question.
May I ask a question?
Please.
So wanted to ask how long it takes, what the time of simulation for magnetic results that you get, you show to us.
You asked me about the time of run.
Yeah, how long it takes, yeah.
Yeah. First of all, do you know that I use Microsoft Office or Advanced Web Research?
Mm-hmm.
Okay. It depends on the grid size and the step frequency. I get this result about 30 to 45 minutes. As you decrease the grid size and decrease the step frequency, you can get more accurate results to be more agreement with the measurements.
Yes, right. Okay, thank you.
Okay, thank you. What kind of what kind of method did you use for simulation in your simulation program? It was FDTD method?
First of all, it is different as compared to CST or HFSS. It is method of movement, based on method of movement.
Yes. Thank you.
Thank you.
Okay, maybe more questions now? Okay, thank you very much for all of you. Let me finish this session and invite you to room A to next session 8A.
Okay, thank you very much.
System Engineering, Computer and Technology. And have a nice sunny day today.
Thank you very much. Have a nice day.
Thank you very much.
Thank you very much.
Thank you to everybody. Thank you to Mr. Chairman.
Many thanks for your cooperation. Goodbye.
Goodbye.
Bye. Thank you, Wojtek. See you somewhere.
See you. Bye, Darius.
Near the border.
Yeah. Okay.
Bye.
See ya. Bye.